Welcome to the next video in electrochemistry. We have equations for you right now. So here are some equations for you. You're familiar with this one before. My delta G0 is minus RT ln K, and this also equals minus NF E0 cell. So E0 cell, you solve for E0 cell is RT over NF, natural log of K. And you can simplify this. So this equation here, the natural log of K, is also 2.303 times the log of K. This is just the natural log of 10. This has to do with what's called the change of base formula when it comes to logarithms. And the reason why we do this is that back in the olden days when we had slide rules in books, like I think the old idea of a nerd came from the people carrying all these big and heavy books, and like among other things, they had logarithm tables. If you read Once and Future King, Merlin and Arthur's and under Arthur, well, under the care of Arthur, well, I should say Merlin was taking care of Arthur. He had logarithm books in his palace when he was with Sir Ector. But anyways, this is a kind of an artifact of the old slide rule and logarithm table days. Now we just have sweet calculators that do all this work for us. If you plug in R equals 8.314, temperature 298.15 Kelvin, Faraday's constant, you get the E0 cell is equal to 0.0592 volts over n number of moles times the log of K. And if you apply the non-standard equation, the delta G0 plus RT ln Q, and you apply that for 25 degrees Celsius, and keeping through 25 degrees Celsius, you have the non-standard equation. The E cell is the standard cell minus 0.0592 V over N log of Q, the reaction quotient. And this is known as the Nernst equation, and it only works for 25 degrees Celsius. So if you change the temperature, you're going to change this equation. So this is the Nernst equation. We're going to use these equations for the next couple examples. So let's start here. Use the tabulated electrode potential to calculate the equilibrium constant for the oxidation of copper by acid at 25 degrees Celsius. So here is the equation there, and you already know how to do this. The E0 cell is negative 0.34 volts. So the E0 cell is 0.0592 over n log of K. So we can solve for K. So that means that NE0 over 0.59, sorry, I missed the 0.0592 is equal to the log of K, which means if you take 10 to this, that gets rid of the log, equals K. So solve for K, and then you can take 10. So N, how many moles of electrons? We have 2 moles of electrons. And then E0 is, I guess I don't, the units are all taken care of by the derivation. E0 is minus 0.34 all over 0.0592. And you put that in your calculator, and you get 3.3 times 10 to the minus 12. So, of course, probably the hardest part of this is the algebra going from here to there for K. So rearranging the equation and then solving it. So that is the equilibrium constant, and it's pretty small. So this is saying this doesn't proceed very far to the right. And we know that copper won't dissolve in acid, so it's not surprising. Okay, now let's do a non-standard condition. To turn the cell potential from a non-standard condition. So here's our non-standard condition. We have copper going to copper plus 2, 0.01 molar with 2 electrons, and permanganate at 2 molar, and 4 acids at 1 molar, and 3 electrons going to MnO2 plus 2 waters. So we got to write the balanced chemical equation first. So we have 2 and 3 electrons, so we're generating 2 and consuming 3, so we need to multiply this one by 3 and that one by 2. So let's go ahead and write this out. So 3 coppers, and I'll include the states, plus 2 Mn. Oh, what am I writing there for? What am I doing that for? Stop that. 2 MnO4 minus aqueous plus 8H plus aqueous yields 3 copper plus 2 aqueous plus 2 MnO2 solids plus 2 water liquids. Okay, so, and this is an aqueous. I'll just make it prettier for you. And while I'm here, I might as well explain the Q. The Q is a reaction quotient. It's products over reactants. It's going to be copper plus 2 cubed all over MnO4 minus squared H plus to the 8th. So that is our Q from this. Also, the N is 6 moles of electrons. Where are we getting 6 moles of electrons? From here, 2 and 3. So let's go ahead and apply the Nernst equation. The Nernst equation is the E cell is the standard cell minus 0.0592 volts over N log of Q. So we have to figure out what the standard cell potential is first. And for this one, using the reduction potentials, the standard cell is 1.34 volts. So you can do that from the looking at the reduction potentials. And this one here, if you must know, this one here is 0.34 volts, and this one is 1.68, based off of the reduction potentials. So these are the reduction potentials, so because of that, this one becomes negative, and you have 1.68 minus 0.34, and you get 1.34. Okay, so now we just put in the numbers. Our non-standard cell potential is the standard 1.34 minus 0.0592 volts over N, 6, log of, let's see here, you have 0.01 cubed all over Mn, so this is 2 squared 1 to the 8th. So 10 to the minus 6 all over 4. So 1 to the 8th is that. So 10 to the minus 6 over divided by 4, the log of that. But anyways, you put that in your calculator, and you get 1.41 volts. So, and this is the non-standard condition, so that's applying the Nernst equation. So, what can you infer from this? Like, well, this, maybe you notice the batteries, when they're new, they work pretty well, and as they're losing their charge, they start to decrease in their effectiveness. This is a supercharged battery. You have copper, you have lots of copper metal, but you don't have very much in solution. And then you have permanganate, you have the cathode there that's going to grow, and there's lots of that in solution. So this is going to have a little bit more, it's going to last longer than if you had it at the standard potential. So this is not surprising that it's a little higher in energy. You probably know this colloquially as well. But so for this one, though, recap, you had to write the balanced chemical equation. I included the states there because the solids and liquids are not included in the equilibrium. So the reaction quotient is the products of the reactants raised their stoichiometric powers, which means it's copper plus 2 cubed over permanganate squared, hydrogen ion to the 8th power. And the number of moles of electrons transferred is 6 because you're generating 2 electrons and consuming 3 electrons. Lowest common denominator between those two is 6. Then you apply the Nernst equation, and put the numbers in, and then you put in your calculator, and you get the answer. Okay? So what? Well, why don't you try this one on your own and see if you can figure it out. And let's talk about some other things. So you can get what's called a concentration cell. Concentration cell, when you have two of the same metal, so in this case, we have copper, and we have copper at different solutions. So this is a standard potential where you have copper all 1 molar. Now, this is a case where we have copper, and you can see the right solution is a little more blue. And what is going to happen with this solution, if you hook it up, you get a small amount of current flowing. The copper metal in the weak dilute solution is going to start going into solution, and the copper, the more concentrated solution, is going to grow, and it's going to continue to grow until the solutions equal out in concentration, and then the potential will be 0. So what? Why do we care? That is how a pH probe works. A pH probe is actually a concentration cell. It's a voltmeter. So when you stick a pH probe, the bottom of it may look something like this. And what you have is you have an electrode and you have a salt bridge. And inside of it, you have a standardized solution. And what a voltmeter is it measures the potential of that solution. And it has it tabulated, so it does the math using the non-standard conditions to figure out what the hydrogen ion concentration is in the solution. And from that, you can tell that from the voltage. The voltage tells us what the hydrogen ion concentration is, and then you can tell the pH. So if you want to have pH probes, you're actually working off this concentration cell using essentially the Nernst equation for that. Okay, so an obvious application to electrochemistry are batteries. So this is on the left here is a dry cell battery. And we typically don't use these anymore. We typically use alkaline batteries, at least for many applications around the home. And alkaline batteries, so if you take one, you saw one in half, this is what they look like. You have a carbon rod in the middle, and that's the cathode, and then that's not necessarily the cathode. The cathode is kind of in the solution. That's just where the stuff absorbs, because graphite is conducting. And you have zinc on the outside of the battery, and you have a gel in the middle. In the gel, there's manganese oxide and potassium hydroxide. And what happens in this battery is the anode corrodes, the zinc corrodes, and then the manganese reduces. So over time, and then typically for this, the battery dies when the zinc runs out. So that's the alkaline battery. If you do decide to do this at home, be very careful, because the paste there has potassium hydroxide in it, and that can blind you very quickly. It can burn you as well, so be careful of that. A car battery, so here's a car battery. Car batteries are lead acid batteries, and if you ever picked one up, they're heavy. So why are they heavy? Well, because they've got lead in them. And the anode is lead metal goes to lead plus 2 ions. It's lead sulfate in solution. And the cathode is lead plus 4 goes to lead plus 2. And the way the batteries work, so it starts off with, if you were to take it apart, you would see one of the anode would be a dull gray, it would be lead metal, and the cathode would be a white container, because it has lead oxide, lead plus 4 oxide. And then when the battery is dead, when it's all used up, you just have the screens in there, and you have lead sulfate in solution. And the solution is going to be it's sulfuric acid, H2SO4. So battery acid is sulfuric acid. And what's nice about lead acid batteries is they're rechargeable. So if you apply electromotive force the other way, you will get the anode and cathode to grow back on in the lead acid battery. And also, what's neat about these, um, they're typically 12 volts, and what you do is you take each cell is about 2 volts, and you have 6 of them in series. We haven't talked too much of the physics of this, but if you put the potentials in series, they add. And so a 12 volt car battery is really 6 cells all in series with each other, bringing it up a total to 12 volts. So, and we so I'm running off a laptop and my iPad and my cell phones. These all have lithium ion batteries. So lithium ion batteries here, and you have the graphite and the anode, the lithium ions, and they transfer over to a lithium transition metal oxide complex. That's the charge and the discharge for a lithium ion battery. And something you've noticed probably, lithium ion batteries, they decrease in their effectiveness over time. And if you really want, so if you want to make your lithium ion battery last a long time, what you need to do is prevent the battery from overcharging. So when you charge the battery, of course, what happens is the lithium ions move from the cathode back to the anode. And if you keep on putting that really negative charge on it, what happens is the lithium ions reduce to lithium metal, and then they react to the interstitial fluids of the battery, and it destroys the inside of the battery that way. So that's the reason why they go down. If you want to make sure your batteries last a long time, don't fully charge them. So I have changed my habits since learning this. I try not to fully charge things, and my cell phone now. I mean, you get the cell phones, and like after 3 years, your cell phone is a paperweight. It doesn't hold a charge for really that much time at all if you do not charge it up all the way. So keep it not fully charged if you can. And I mean, if you're like going to go on a long plane ride and you want to play on your phone or your iPad, then yeah, charge the sucker up all the way. But if every day you're charging it to 100% and leaving it plugged in overnight, that's going to destroy the battery over the period of months to years. So that's the user's fault in that. It'd be nice if they had a program to prevent the charging at a certain point in time, but I guess I don't know. Maybe they do for the Macs. I'm not sure. That would be a nice feature. Okay, and what about fuel cells? So fuel cell technology is old. We've been using it since about the 1960s. It was part of our space program because astronauts. It powered the space shuttle and the Apollo spacecraft because the water for astronauts to drink came from a hydrogen fuel cell. And man, that's a tough job. Whew. Being an astronaut, you got to wait for your fuel cell to put out water to be able to drink something or eat something because the food was dehydrated. So, anyways, the way that they work, and this is the old technology. Nowadays, we're trying to make these less expensive because the anode and cathode they're on pieces of platinum, and platinum are expensive. So what we've been doing is we've been using something like a zeolite. That's the same stuff they put in car exhaust in the catalytic converters. So and they put nanoparticles, platinum or palladium nanoparticles. And the idea is the hydrogen goes and absorbs on the platinum palladium nanoparticles, and it breaks apart into hydrogen ions, and the hydrogen ions transport across to the surface on the cathode, and then the hydrogen ions transfer over to the platinum or palladium nanoparticles, and then it reacts with oxygen, and then water comes out, and as the ions are flowing, the electrons flow, and then does work. So that's just it's hard to do, and it's getting these hydrogen to break apart into hydrogen ions and then transport through some fluid to the other side and reappear on the surface to react. That takes some pretty gnarly chemistry. I mean, it's just hard to do. And I mean, we have them, we use them, but they're very expensive, right? I mean, the fuel cells, the big fuel cells that we had, I mean, they're huge. The ones they use in the Apollo space program. We've gotten them smaller, but we're still trying to make it better, and we can't really figure out how to use it yet, and to power things like a car. But what we can use them for are for breathalyzers. So if you've ever used a breathalyzer, at least the ones the police use, I personally have never been breathalyzed, but these are fuel cells. And the idea is the amount of ethanol in your breath can then determine your blood alcohol level when you have the fuel cell breathalyzer. Like so, so this is actually using a fuel cell to backtrack there. So interesting stuff. So I got one more talk for you. So please join me for the next lecture.